Hi, my name is Mark Holtzapfel, and I'm a professor in the Chemical Engineering Department at Texas A&M University. What we're going to do during the next few hours is talk about chemistry. Now, for many of you, chemistry probably is a subject that you had 4, 5, 6 years, maybe even longer, and you probably forget it as soon as you could, because a lot of people really don't like chemistry. Well, what we're going to do is in the next 2 hours take all of your freshman chemistry plus a little PChem, physical chemistry, and organic chemistry and condense it into a 2-hour review session. So we have a lot of work ahead of us. The topics we're going to discuss today are some basic concepts in chemistry, molecular bonding, the ideal gas law, which you've probably seen in your thermo courses, concentration measurement in solutions, pH associated with acids and bases, chemical reactions, and a brief review of organic chemistry. Well, let's start at the beginning. The beginning is with the atom. And what I'm using here is a lithium atom because it's rich enough to have some different features in it. Notice in the nucleus, what we have are two species. There's a proton indicated in black and a neutron indicated in white. And then surrounding that nucleus is an electron cloud. Here we have an inner cloud with 2 electrons, and then we have an outer cloud with just a single electron. And what you'll notice is that the 3 protons are balanced by 3 electrons, so this particular chemical species is neutral. Now let's talk a little bit about these different chemical species. In the nucleus, we have the proton, which is positively charged. It weighs a very, very small amount, 1.6 times 10 to the minus 24 grams. We can call it also an atomic mass unit, so it's a little over 1 atomic mass unit. An atomic mass unit is defined as 1/12 the mass of a single atom of carbon-12. Now the neutron is a neutral particle, and it weighs a little bit more than the proton, and here it is also expressed in atomic mass units. So you can think of an atomic mass unit as almost the mass of a single proton. Now the electron is of course negatively charged, and it has a very small mass. You can see it's much, much less than 1 atomic mass unit. Now these electrons are arranged into inner shells and outer shells, and you can see in the lithium example, here are the 2 inner shell electrons, and then there's that 1 outer shell electron. The inner shell electrons are very stable. They're close to the nucleus and generally non-reactive. It's the outer shell electrons where all the action is. The outer shell electrons are also called the valence electrons, and you can think of chemistry as the study of valence electrons, which is the point that's made right here. Now let's get a few definitions under our belt. The first is atomic mass, and that's the total mass of all the protons plus neutrons, plus electrons in a single atom. The atomic number is the number of protons in the nucleus. A neutral atom has the same number of protons as it has electrons. An element is all those atoms with the same atomic number. They're grouped together and called an element, such as iron, for example. And then another definition is an isotope. The various elements can have a variety of atomic masses, and to illustrate that, let me use carbon as my example. These are the isotopes of carbon. Notice at the top of the list we have carbon-10 ranging all the way up to carbon-16. Now notice that they all have 6 protons because by definition carbon has 6 protons, and these carbon atoms are neutral, so there are 6 electrons to balance out the positive charge of the protons. Where we get the variety is in the neutrons. We have a range from 4 up to 10 neutrons in these carbon isotopes, and you can see where the number comes from. If I add the number of neutrons to the number of protons, in this case I get 10, so we call that carbon-10. In this last case we have 10 neutrons and 6 protons. We add those together and we get carbon-16. Now, some of these carbon species are stable. They will be with us for the rest of the universe, essentially. Carbon-12 is very stable. It doesn't have a half-life. And carbon-13 is also very stable. And you can see the relative abundance in our planet. 98.89% of all the carbon that you find is carbon-12, and a little over 1% is carbon-13. And you can see the atomic mass of each species indicated here. Notice that the mass of carbon-12 is exactly 12 because it's by definition. So if you go to a periodic table and they list the mass of carbon, this is the likely number that you'll find, which is sort of the weighted average of these two atomic masses. Now, carbon-10, the first carbon that's shown, has a half-life of only 19 seconds. Carbon-11 is 20 minutes. Carbon-14 is almost 6,000 years. Carbon-15 is 2 seconds, and carbon-16 is 0.7 seconds. Before we go any further, let's just talk a little bit more about half-life. Half-life is when you have a chemical species A and is converted into chemical species B. The rate of this reaction can be described as the rate at which A is destroyed, or it can be described as the rate at which B is generated. And in this particular case, it's a first-order reaction, which means it's proportional to the amount of A that you have. So let's look just strictly at species A for a moment, so we can disregard B for this derivation. So we have the rate at which A is destroyed is proportional to KT, and what I've done is I've taken, by separation of variables, I've taken the A over to the other side and the dt over to the other side. So that's how I got to this step. Now what I'm going to do is integrate this expression. This is the integral of dA over A. Put in the bounds, use the rules of logarithms, take exponent of each side. And so what we're left with is the amount of A that you have at any time t is equal to the amount you started with multiplied by this expression right here. Notice that this is a negative, so as time gets larger, the amount of A that you have goes down. Now, if we define tau as the half-life, that's the case where the amount of A that you have divided by the amount you started with is equal to 1/2. So we can substitute that into our expression and then solve explicitly for K, which is right here. Plug that K in up here. So this is an alternative expression for the amount of A that you have given the half-life. So again, going back to our isotopes, we have a variety of half-lives. Again, the half-life tells you how long it takes for half of the stuff to remain. So let's say, for example, I start with 1 gram of material. Let's say it's carbon-10. What that means is that in 19 seconds, I'll have half a gram, and in another 19 seconds, I'll have a quarter of a gram, and so forth. Now, it turns out that this property of half-lives is very, very useful. And let's imagine for a moment that we're Indiana Jones. And what we've done is we've broken into a pyramid, and what we find inside of that pyramid is a boat. What the Egyptians used to do is bury their dead in a boat, and the idea was that this boat would take their souls to the netherworld, that is, into heaven. So you find this boat in the pyramid, and what you'd like to do is figure out how old it is. So what you do is you take out your trusty pocket knife and take off a little chunk of this boat and bring it back to the laboratory. Now the idea is that with half-lives, you can figure out how old the boat is. This is the logic behind it. Here we have the Earth. This is the atmosphere surrounding the Earth, which is composed primarily of nitrogen. And we have these cosmic rays impacting on the nitrogen, which transform it into carbon-14. Then we have a tree, which is busy growing on the surface of the Earth. And what happens is the carbon-14 that's in the atmosphere ultimately ends up as carbon dioxide. It'll burn up with the oxygen in the atmosphere, and that carbon-14 will get incorporated into the wood of that tree. So the idea is that this background radiation is relatively constant, and we're always producing some carbon-14 in the atmosphere, so there's going to be a certain percentage of the carbon in the wood that is carbon-14. So what happens is that once it gets incorporated into the wood, it immediately starts decaying, and in this case, the half-life is 5,730 years. So if, let's say, for example, that 0.1% of the carbon in wood is carbon-14, and you find out that your sample has 0.05% carbon-14, you can say, aha, that sample is just about 6,000 years old. So this is the principle behind carbon-14 dating of archaeological artifacts. Now, so we've just spent an awful lot of time talking about carbon to give you a sense of the variety of isotopes. The elements, as you recall, differ in their atomic number, which is simply the number of protons in the nucleus. And I've listed here for you all the known elements, or almost all the known elements, and I've also listed the atomic mass in atomic mass units. Just a few points. For example, sodium, why is Na the symbol for sodium? Well, the Latin name for sodium is natrium, so that gives you the Na. Potassium is kalium, so that gives you the K. Iron is Ferrum, which gives Fe. Copper is cuprum, Cu. Here's an interesting one. Silver, which is abbreviated Ag, argentum, looks an awful lot like Argentina. And where Argentina came from, the name, is that it had a lot of silver, and so they named it after the silver that was found there. Related to silver in terms of precious metals is gold, which is abbreviated Au. Here we have lead, plumbum, which I think is just an interesting word to say. And we go on up into the higher ones. The highest naturally occurring element is uranium, atomic number 92. So all these what are called transuranic elements are manufactured in a laboratory. They all have a half-life, which means they're going to decay, some very, very rapidly, and these are all artificial. You can see they have a variety of interesting names like Einsteinium, Mendelevium, Nobelium, and so forth. So they're named after people. Well, the electrons, you can think of them as quote-unquote orbiting the nucleus. That's actually a rather primitive vision of the atom. That was a vision we had maybe at the turn of the century. Now what we do is we think of the electrons as having a cloud surrounding the nucleus. And you can think of this cloud as the region where there's a probability of finding the electron. So if we say I'm going to set a 95% probability, what we're saying is that within this shell, there's a 95% chance you'll find the electron somewhere in there. The way that you define those probabilities is you use the Schrödinger equation, which is really beyond the scope of this brief review. Now, the regions where you find the electrons are called orbitals, and one type of orbital is called the s orbital. It holds 2 electrons. It has a very, very simple shape. The solution to the Schrödinger equation for the s orbitals is simply a sphere. Then we have what are called the p orbitals, and the solution to the Schrödinger equation here, which gives again the probability of finding the electron, looks like 2 lobes, one that's on the x-axis, one is on the y-axis, and the other of these pair of lobes is on the z-axis. Next we can go, and by the way, the p orbital holds 6 electrons, 2 in each of these. Next we can go to the d orbital. There's 5 shapes for those, which you can see here. Each of these orbitals also holds 2 electrons. And I have here the f orbital with 14 electrons. I indicate that it's too complex to show, but I in fact did find a reference that shows the f orbitals. And you can see those here. So the f orbitals are shown at the bottom, and these also have very complex shapes. So again, the idea of these orbitals is it's where you are likely to find the electron as it quote-unquote orbits or buzzes around the nucleus. Now, what I'm going to be doing for the next few minutes or so is actually building elements for you. So the idea is that hydrogen has just a single electron that goes into the 1s orbital, which again, remember the s orbital looks like a sphere. Then when we add the second electron, we get helium. That second electron goes into the 1s orbital. Now that 1s orbital is filled up, so when we add our third electron, we're going to put it into another s orbital, fill it up, and we get beryllium. Then as we add another electron, we're going to now start working on the p orbitals. Recall the p orbitals can hold up to 6 electrons. So as we go down this, the boron, copper, nitrogen, oxygen, fluorine, and neon, where we're adding those extra electrons is now into the p orbital. Now you might be asking yourself, Dr. Holzapfel, why is it that we put the electrons into the s first, and then you put some more into the s, and then the p, and now we're going to go back to the s, so what's the logic to it? Well, there's a little simple pattern that you can use. If you write the orbitals like this, we fill them in this way. So the idea is we're working on the 1s orbital here. Once it's filled up, we're now working on the 2s orbital. Now that it's filled up with beryllium, now we'll start working on the 2p orbital. Right here, it holds 6 electrons. And then when we fill that up, we'll start working on the 3s orbital. So this simple pattern can help show you at least some logic to the order or sequence in which we fill up these atoms. Now once we get to neon, we have filled up the inner 1s orbital, and we have filled up the 2s and the 2p orbital, so that we have a total of 8 electrons now in the outermost shell of neon. It turns out that this is very, very stable. This is a recurring theme in chemistry, is that 8 electrons in an outer shell are very, very stable. Neon is a stable noble gas, meaning it's non-reactive. It has all the electrons it wants in the outer shell, so it's happy. Now as we add more electrons, we're going to start working on sodium, magnesium, aluminum. So we filled up the 3s orbital. Now we're going to start working on the p's again. So it's the same story. We just keep filling up electrons. Here we have our 8 electrons in the outermost shell. That is argon. Again, argon is a stable noble gas. It's very non-reactive, and we can just keep building them up here. So it's the same story. I won't go on and on about the details. So here's just, you can see briefly some other ones. And finally we've filled up to uranium and beyond. Now, as I mentioned before, the electrons in the inner shells are basically inert. So in this case, all these electrons in the radon shell are inert. Where all the action is these outer electrons, which again are called the valence electrons. People realized 100 years ago or more that different elements have similar properties, and by arranging them into what's called a periodic table, you can see the similarity between these various elements. So here is the periodic table. I'm sure you've all seen it. It's very familiar. Again, as we were, let me zoom out here. Here we were working on the 1s orbital. We've completed the 1s orbital. Now we were adding electrons. We're working on the 2s orbital. Here we were working on the 2p orbital, 3s orbital, 3p, 4s, now the d, back to the p. So you can see that the periodic table all of these elements in this column are filling the s orbitals. These are filling the p orbitals. All of these are working on the d orbitals. And the ones down here, which are sort of inserted to here, are as you fill up the f orbitals. And the idea is that, let's say we take fluorine and chlorine as an example. They both have 7 electrons in the outermost orbital, and so they have very similar chemical properties, so they're listed in a column. So the way it's arranged is the noble gases, which are shown here in the rightmost column. Remember, those are all filled up. They've got 8 electrons in the outer shell. They're very stable, non-reactive. They really don't want another electron. The alkali metals, which are shown right here, except for hydrogen, which is not really an alkali metal. These alkali metals have a similar property. They're metallic in character, and if you put them into water, the water becomes basic. Over here we have the halogens in this column. The halogens are non-metallic. They'll form readily with hydrogen to form acids, such as hydrochloric acid or hydrofluoric acid. So again, the idea is by arranging elements that have similar properties into columns, we can create some structure and order out of the periodic table, or out of all these elements. Now, I've been throwing around the word metal without really defining it very well. Metals are defined to have a silvery luster. They're good conductors of heat and electricity because the outermost electrons are very loosely bound, and it's easy for them to flow by putting a voltage gradient on them, for example. Elements to the left of the heavy line are metals, and elements to the right are nonmetals. So if we go back to our periodic table, you can see right here is a heavy line, and the idea is that everything to the left of this heavy line is a metallic, and everything to the right is non-metallic. Now, I'll let you in on some I guess some secrets or some key ideas here. Chips or semiconductors are extraordinarily important to our economy in the information age. And here we have silicon located right there. Most of the chips that we use nowadays are based on silicon. And silicon has 4 electrons in its outer orbital. You can see that. 1, 2, 3, 4. And so it's halfway to 8. And it turns out that if you have 4 electrons in your outer shell, it's a little bit stable, not as stable as if it were argon, but it's pretty stable. Now, the idea of these chips is that we create a sea or an ocean of silicon, and then we can dope it very lightly with either aluminum or phosphorus. Now, the idea is that phosphorus has 5 electrons in its outer shell, so it has 1 more than 4, and it would like to shed that extra electron if it could. And here we have aluminum, which has 3 electrons in its outer shell, and it sure would like to gain an electron. So if, for example, here we have our ocean of silicon, and then we dope it with some aluminum, and right across from this junction we have some phosphorus. What will happen is electrons will jump from the phosphorus to the aluminum. So now the phosphorus has 4 electrons and the aluminum has 4 electrons. Now the aluminum will pick up a negative charge as a result, and the phosphorus will become positive, but they're all trying to have 4 electrons in the outer shell, and that's the basis of semiconductors. That's how they work, is this jumping of electrons across a potential. Now, one of the most famous concepts in chemistry is called electronegativity, and this concept was developed by Linus Pauling, who's a very remarkable individual. He actually has 2 Nobel Prizes one for his work in chemistry and one for his work in peace. You may be familiar with Linus Pauling because he's been an advocate of using vitamin C to ward off cancer, for example. It's somewhat controversial, but I would say many people now agree that taking large doses of vitamin C is a good thing to do. What vitamin C does is it protects you from free radicals, and I'll be talking in a few minutes about free radicals. The idea is that the normal activities that we do every day, let's say breathing in air or running or walking around, what happens is the oxygen becomes a free radical, and it wants to react with anything it can in the cell, including your DNA. What the vitamin C does is it acts like a sponge and sucks up those free radicals and prevents them from doing or minimizes the amount of damage that's done to your body. So Linus Pauling says by taking megadoses of vitamin C, meaning literally grams per day, you can minimize the amount of damage that's done from everyday living. I personally take about 2 or 3 grams of vitamin C per day, and I also take vitamin E because it helps ward off free radical damage in the fats in my body. Now, getting back to Linus Pauling and his electronegativity concept, he uses a 4-point scale, and here we have the periodic table, and underneath each of the elements you'll see a number that tells you the affinity that that element has for electrons. And what you should notice is that fluorine, which is up here in the right-hand corner, has the strongest electronegativity, 4. And you can also see there's a pattern. As we go from left to right, we increase our electronegativity, and as we go from bottom to top, we increase our electronegativity. So fluorine is in the upper right-hand corner. It is the most electronegative compound. And here we have francium down at the bottom left having a very low electronegativity. You can think of electronegativity as the strength with which an element will grab onto an electron. So if, for example, we have a battle or a combination of, let's say, hydrogen and fluorine, you can see that the fluorine has an electronegativity of 4.0 and the hydrogen is 2.1, so that electron cloud that's swarming around the hydrogen, and also this electron cloud swarming around the fluorine, what's going to happen is the fluorine is going to suck over those electrons, so the fluorine is going to become somewhat negative, and the hydrogen will become somewhat positive because the hydrogen, being kind of a wimp, is somewhat stripped of its electrons by that bully, the fluorine. So this concept of electronegativity explains a lot of principles that we find in chemistry. So that gets us to our next topic, which is molecular bonding. A molecule is defined as an aggregate of atoms, the smallest unit of a macroscopic substance that retains all the chemical properties of that macroscopic substance. So another concept that you come up with that's related to molecular bonding is molecular weight, which is the sum total of all the atomic weights in a molecule. So for example, if I looked at calcium chloride, it's got 1 calcium, which weighs 40.08, and it's got 2 chlorines that weigh 35.453. Add them up, so the molecular weight of calcium chloride is 110.986. If we look at methane, it has 1 carbon and 4 hydrogens. It has a molecular weight of 16. And here's magnesium sulfate with 1 magnesium, 1 sulfur, and 4 oxygens with a molecular weight of 120. Now, when we start taking elements and combining them together, we can form molecules. So if we have a case where the 2 things that you're putting together have similar electronegativities, we have what's called a covalent bond, and if they're widely different, we have an ionic bond. So let's go back to this table of electronegativities and take a look at hydrogen. Hydrogen is 2.1 and sulfur is 2.5. So those are very similar, and what that means is they behave very gentlemanly. This hydrogen shares its electron with the sulfur, which in turn shares its electrons with the hydrogen. So for the most part, there's not very much charge on this. the electrons pretty much evenly surround the nuclei. Now let's look at another extreme. Sodium, it has 0.9 as its electronegativity, and chlorine is 3.0. What you can see is there's a wide disparity between the electronegativities. The chlorine is the bully here. It takes the electron from that sodium. In fact, it takes it so strongly that the chlorine takes on a negative charge, and the sodium, having lost its electron, takes on a positive charge. Now, getting back to this topic of covalent bonds, there are three types of covalent bonds that we encounter. One is called a single bond, and here we're showing ethane as an example. Here's the carbon, another carbon, and it's surrounded by hydrogens. Now recall that where carbon is in the periodic table, carbon is located right here. It has 1, 2, 3, 4 electrons in its outer shell. So I'm indicating the valence electrons of carbon, this carbon, as closed circles. So you can see that there are 4 there. And this carbon also has 4. I'm showing those as open circles. So there's 4 of those. And if we take a look at hydrogen, hydrogen just has 1 electron in its outer shell. I'm showing the hydrogen electrons as X's. Now look at, by doing a single bond, recall that what we'd like to do is have 8 electrons in the outer shell because it's stable. It behaves in a sense like the noble gases. So by arranging the atoms in this way, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around that carbon, 1, 2, 3, 4, 5, 6, 7, 8 around that carbon. Now hydrogen only needs to have 2 electrons to be stable, so this one has 2, 2, 2, 2, and so forth. So everybody's happy. We've got 2 electrons around the hydrogens and 8 electrons around the carbon. Here we have an example of a double bond, and in this case ethylene is our molecule. Again, we have 4 outer electrons around this carbon, 4 around that carbon, and then the 1 associated with the hydrogen. By arranging them in a double bond, you can see that we have 1, 2, 3, 4, 5, 6, 7, 8 for this carbon, 1, 2, 3, 4, 5, 6, 7, 8 for that carbon, and again, each of the hydrogens has a single, or a pair of electrons, so that becomes stable. We can also have a triple bond. This is acetylene. Again, there's 1, 2, 3, 4 electrons from this carbon, 1, 2, 3, 4 from that carbon, 1 electron from that hydrogen, 1 from that hydrogen. This carbon has 8, 1, 2, 3, 4, 5, 6, 7, 8. This carbon has 8, 1, 2, 3, 4, 5, 6, 7, 8. And each of the hydrogens has 2, so they're happy as well. Now, I mentioned earlier in my discussion of Linus Pauling and vitamin C, I mentioned the word free radical. And what always comes to my mind is I think of the 60s where you free the radicals. Well, in the chemistry context, this is not what we mean. A free radical in the chemistry context is an atom that does not have a complete shell. So let's take a look, for example, at chlorine. Chlorine is located here on the periodic table, which means it has 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. But it wants to have 8. So it is extraordinarily reactive. What this free radical chlorine will do is seek out anything that it can react with. For example, if you have another free radical of chlorine with its 7 electrons, by these 2 combining together, now we can have satisfied. If we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around this chlorine, and again 8 electrons around that chlorine. So the idea is if you have an atom that's not satisfied with 8 electrons or 2 electrons, in the case of hydrogen, it's extraordinarily reactive. It wants to find a partner to get together with. In this case, two of these free radicals get together to form dichlorine. Just as an aside, this chlorine free radical is very, very important in our environment. What happens is that if you have ozone, which is formed up in the atmosphere It's a shield from ultraviolet light. In the presence of a chlorine free radical, what happens is the ozone is destroyed and it becomes elemental or a diatomic oxygen again. And so what's happening is you're taking this very useful species of ozone, which protects us from UV light, and turning it into ordinary oxygen, which does not protect us from UV light. The consequences of that are that there's likely to be more skin cancer, potential damage to crops, and so forth. To show you how potent that chlorine-free radical is, it actually acts as a catalyst, which we'll talk about a little bit later. That single atom of chlorine will destroy roughly 20,000 to 100,000 ozones before it's taken out of the system. So it's extraordinarily destructive. Getting back to our free radical discussion, this is a free radical of oxygen, which is in our bodies. It does a lot of damage. By taking vitamin C, we can suck up those oxygen free radicals. In this case, two of these free radical oxygens are getting together to form diatomic oxygen. Again, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around each of those nuclei. There are many examples of atoms that get together and form diatomic species, nitrogen, oxygen, and a variety of halogens. And I could add to that list hydrogen as yet another example. Now, chemistry can be very confusing. So previously we talked about free radicals, which are uncharged species that are very, very reactive. Another concept is radicals, and it unfortunately has a similar name, but it is a different concept than free radicals. Some elements form what are called stable species. For example, if I combine 1 nitrogen and 3 oxygens together, that is a stable species, and it happens to have picked up an extra electron, so it has a -1 charge. In the case of sulfate, 1 sulfur and 4 oxygens get together. It picks up 2 extra electrons. It has a -2 charge. Here we have carbonate, 1 carbon, 3 oxygens. It picks up 2 extra electrons, so it has a -2 charge. And phosphate would be 1 phosphorus, 4 oxygens, and it picks up 3 extra electrons and has a -3 charge. Okay, let's shift gears a little bit and talk about the gas laws. There's a concept called an ideal gas, and what we mean by an ideal gas is it has no intermolecular forces and the gas molecules occupy no volume. In reality, there is no such thing as an ideal gas, but real gases will behave like ideal gases if we have a very low pressure, and also as we go to high temperatures, gases behave as ideal gases. Now, the ideal gas law describes the relationship between pressure, volume, moles, and temperature. And there's 2 types of systems that typically are used, scientific units or engineering units. In the scientific units, likely pressure or pascals would be used as a unit for pressure. And in the engineering system, PSI would tend to be used. In scientific units for volume, we would tend to have a liter or perhaps a cubic meter. And in the engineering system, cubic feet. In the scientific units, we would tend to use a gram mole. Engineering units would use a pound mole, and I'll talk about that in just a second. And then with the temperature, the scientific units tend to be Kelvin, and in the engineering units, Rankine. Now, let's talk a bit about some common problems when using the ideal gas equation. I'd like you to notice that the pressure must be the absolute pressure, and the temperature must be the absolute temperature. And what we mean by that is, let's think about pressure for a moment. Pressure is from the pounding of molecules on the wall of a container. So if this is the, I'll use my hand as one wall of the container and my other hand as a molecule, when that molecule hits the wall, that is the absolute pressure. What is the total force that that molecule is in pounding the wall? That's what we mean by absolute pressure. In the case of absolute temperature, what we're talking about is what is the temperature of the gas compared to absolute zero, which is the temperature where as cold as you can get. Some people think it's the temperature where motion stops. That's almost true. There's a little bit of residual motion at absolute zero. So absolute zero is where that's the coldest temperature you can get. And so when we're talking about absolute temperature, it's the temperature scale where zero is assigned to absolute temperature. Now let's zoom in on some of these formulas. If you are given the pressure as a gauge pressure, what you do is add 1 atmosphere to it. 1 atmosphere is 14.69 psi, and that'll get you your absolute pressure. If you are given a temperature in degrees Fahrenheit, you add essentially 460 to that, and that'll give you the Rankine. If you're given temperature in degrees Celsius, add 273.15, that'll get you into Kelvin. If you want to go from Celsius to Fahrenheit, you use this formula. If you want to go from Fahrenheit to Celsius, you use this formula. Okay, so that keeps track of absolute pressure and absolute temperature. Now let's get back to this idea of moles. And I would say if there's one concept that students tend to get confused about in chemistry, it's moles. By definition, a gram mole is equal to this number right here. 6.022 times 10 to the 23. If you're comfortable with the concept of a dozen or a gross, you should be comfortable with the concept of a mole because it's just a fancy word for that number. Now, where did that number come from? The idea is that, let's say that we had 12 grams of carbon-12. And we have some tweezers that we can count those individual atoms of carbon-12. As we count those 12 grams of carbon-12, the number that we're going to get is this number right here. And it has another name. It's called Avogadro's number. Now, if we were to, in the engineering system, rather than gram moles, we talk about pound moles. In the engineering system, if we had 12 pounds of carbon-12, and we start counting how many species there are, we will end up with this number. So a pound mole is just an abbreviation for this number, and a gram mole is an abbreviation for that number. Now, the way you can calculate the number of moles you have is you say, what is the actual weight of the species that I have, and you divide it by the molecular weight, and that will tell you how many of those moles that I have. Now, there's a concept in chemistry called standard temperature and pressure. Standard temperature is 0 degrees Celsius, and standard pressure is 1 atmosphere. If we take the ideal gas equation and rearrange it so we have volume per mole is equal to RT over P. This is the ideal gas constant, which varies depending on what system you're using. There is the temperature, and what we've done is we've shifted from Celsius to Kelvin, because remember, it has to be absolute temperature. And then the pressure is 1 atmosphere. What we find is we have, if we have 0 degrees Celsius, 1 atmosphere, there are always 22.4 liters of ideal gas in a gram mole. This concept is really quite remarkable. Let's say that I have 2 grams of hydrogen. What that means is if I have it at standard temperature and temperature and pressure, it'll occupy 22.4 liters. Now, there's a very, very heavy gas called uranium hexafluoride. And it has a very high molecular weight, which I'm frantically trying to find here. Okay, uranium hexafluoride has a weight of 352. Now, this concept of a mole, in the case of hydrogen, if I have 2 grams of hydrogen at STP, it'll occupy 22.4 liters. If I have 352 grams of uranium hexafluoride, it also will occupy 22.4 liters per gram mole at standard conditions. So that's an enormous difference in mass or weight, but the idea is that each of these atoms is very, very heavy. I mean, uranium is the heaviest naturally occurring isotope or element. It has an enormous weight, so each of those gas dots has a very, very high mass. Incidentally, if there are nuclear engineers out there, uranium hexafluoride is used to separate different isotopes of uranium. There are 2 common isotopes of uranium, 238 and 235. 238 is about 99.3% of all the uranium that you find, and the 235 is 0.7%. It turns out this is the useful one. This is, for most purposes, considered trash. And so what you have to do is separate the useful 235 from the non-useful 238. So by reacting uranium with fluorine, you can make a gas, and once it's a gas, you can separate the heavier one from the lighter one in centrifuges or membranes and other such technologies. Okay, we've been talking about the ideal gas law, and common types of problems that you'll encounter on EIT exams relate to taking a gas that's at condition 1 and changing the properties, let's say the temperature or pressure, so it goes to condition 2. So for example, this table that I'm showing you says, let's say that I have a process occurring at constant temperature and constant pressure. The volume and pressure, let's say we start here, constant temperature. The volume and pressure are related in this way, so that as the volume goes up, the pressure goes down. If we have a process at constant pressure, the volume and temperature are related to each other linearly or proportionally, so as volume goes up, temperature goes up, provided we're at constant pressure. Let's take a look at another example. A constant pressure process, temperature and volume are related this way. At constant volume, pressure and temperature are the same. So if I double my temperature, the pressure will double, provided I have constant volume. And here's another case, constant temperature. Notice these are inversely related. So if my pressure doubles, the volume goes in half. So these are famous types of problems. A classic example would be, let's say that I have a gas cylinder sitting on the loading dock in the morning. The temperature might be, let's say we'll put it in Celsius degrees, or Kelvin degrees. Let's say it's 280 degrees Kelvin in the morning, and then in the afternoon, the temperature goes up to 300 degrees Kelvin. Now there's a pressure gauge located on the cylinder. Of course, the volume is constant, so we're dealing with this situation, constant volume. And what we're doing is we're trying to figure out the relationship between temperature and pressure. So what this says is that the pressure ratio is 300 to 280. So if in the morning I had, let's say, 10 atmospheres of pressure, by afternoon it'll go up to this ratio of 300 over 280. So the pressure in the afternoon would be 10 times 300 over 280. So from this simple example, there are lots of problems can be built and used in the EIT exam. Okay, we're done talking about gases. What I'd like to do now is talk about measuring concentration. And before we do that, we have to get a few definitions under our belt. The first is solute, and the definition is that which is being dissolved, for example, salt. Solvent is that which does the dissolving, for example, water. And solution is the homogeneous mixture of solute and solvent. And what we mean by homogeneous is that no matter how small you divide it, the chemical composition is the same. So now we're ready for some definitions of concentration. One is molality, and it's defined as how many gram moles of solute you have per kilogram of solvent. It's abbreviated little m, and the picture you should have in mind is here is 1 kilogram of solvent, for example, water, and here we have our solute, the salt. I have 1 gram mole of that, so when I dissolve 1 gram mole of salt into 1 kilogram of solvent, water, then I have, by definition, a 1 molal solution. Now let's take a look at another example. Molarity, which is abbreviated capital M, is defined as gram moles of solute per liter of solution. And the picture that you should have here is I've already dissolved my gram mole of salt into my water, and after it's all done, I have a volume of 1 liter. So you can think of the molality as you haven't mixed it yet, but the molarity is you have already mixed it. And notice also that molality has a weight basis. It's really a ratio of the moles of solute to the mass of solvent. And here we have how many gram moles of sugar or salt are dissolved in a volume of solution. Well, those are fairly straightforward definitions, but what gives people a lot of trouble is normality, which is abbreviated capital M. And I went to my chemistry textbook and looked up the definition of normality, and it says gram moles of equivalent electrons per liter of solution. And I look at that definition and say, what the hell is an equivalent electron? Well, Dr. Holtzapfel comes to the rescue and comes up with his own definition of normality, shown here. My definition is it's gram moles of solute per liter of solution times the change in valence, and this is indicating absolute value. Now let's take a look at this. Gram moles of solute per liter of solution, well, that's the same thing as molarity. So what I'm going to be doing is multiplying my molarity by some integer, which is the change of valence. So let's look at an example. Here I have 1 gram mole of salt dissolved in 1 liter of solution. So we would say that that is a 1 molar solution based on our definition up here. And notice that each of these ionic species has a +2 charge. Then we're going to carry out a reaction. We're going to add something that strips away 2 electrons from each of these ions, so now they have a +4 charge. If we look at this definition, we say normality is the gram moles per liter of solution times the absolute value of the change in valence. So what we have here is 1 gram mole of solute per liter of solution, and the change in valence is from 4 to 2, absolute value. So we say that that is a 2 normal solution, and by the formal definition, that's 2 gram moles of equivalent electrons per liter of solution. Now what we're going to do is start with the same situation, 1 gram mole of salt dissolved in 1 liter of solution, and also with a +2 charge, but we're going to carry out another reaction. This reaction adds 1 electron to each of these ions, so now we have a +1 charge. Using Holtzapfel's definition of normality, we say it's 1 gram mole per liter of solution times the change in valence. Now this time it's from 2 to 1, absolute value, and so this time we would have a 1 normal solution. So what's implied in this definition is you must have a reaction of some sort, and the reaction must cause a change in the charge of the ionic species. Now, a common way that you will hear about normality is with acid bases. So let's imagine that I have hydrochloric acid, and I'm going to react it with sodium hydroxide. What will happen is I will end up making sodium chloride plus water. If I have a 1 molar solution of hydrochloric acid, my question is, what is the normality of that solution? Well, if you take a look at what's happening here, I've got a hydrogen with a +1 charge, and when it reacts, when it forms a covalent bond with water, it essentially has a 0 charge. So the change in valence is from a +1 to 0, and using Holtz-Appel's definition, the normality is equal to this 1 molar times the change in valence, and so that 1 molar solution would be a 1 normal solution. Now let's take a look at another example. In this case, sulfuric acid, and we're going to react 2 sodium hydroxides with that to form sodium sulfate. Again, I'm going to start with a 1 molar solution of the sulfuric acid, and the question is, what's the normality? Well, we can use the same logic. I have 2 +1 charges over here, and here I have 2 0 charges because it's in a covalent bond. So that means the change in valence is 2. I started with a 1 mole, and so that becomes a 2 normal solution. Let's use one last example. Phosphoric acid. It's like this. We react 3 sodium hydroxides, and we get again, hopefully by now you're getting the idea. We're starting with a 3 positive charges and now going to 3 neutral charges. The change in valence in this case is 3. If I start with a 1 molar solution, the normality of this would be a 3 normal solution. Now you might ask, this seems crazy. Why don't you just describe molarity or molarity all the time? The idea is that you can differentiate because sometimes there are weak reactions. You might have a case where this phosphoric acid, if you don't have a strong base like sodium hydroxide, you can actually end up with, let's say, sodium and then 2 phosphoruses. That would have a +1 charge, and this would have a -1 charge. So in this case, if that was the reaction, a 1 molar solution of that would be equivalent to 1 normal because there's only 1 change in charge. So again, one of these hydrogens has a +1. It's becoming a neutral one, so in that case, there's only this 1 molar solution. If that's the reaction, would be 1 normal. You could have another case where in this case, a 1 molar solution of that would be a 1 molar would give 2 normal. I know it's very confusing, but that's the way the chemists do it. Okay, let's talk about pH. pH is an interesting concept. It's something that the general public is familiar with. In fact, there's some shampoo commercials where people talk about pH balanced shampoo. So it's in the general knowledge. Water dissociates, that is, it spontaneously breaks apart into a proton, which we symbolize as H+, and a hydroxide ion, and it's an equilibrium. Now, anytime you have an equilibrium, you can write the equilibrium as products divided by reactants. So in this case, the products are a proton and a hydroxide ion, and the reactant is water. And it's equal to a constant, the equilibrium constant. Now, and we use these square brackets to indicate concentration expressed in molarity. Now,